This video covers the concept of uncertainty in project management. Uncertainty revolves around the completion time of individual tasks. So if you have, it's rare that we have full predictability about exactly how long something is going to take, and then when we incorporate some uncertainty, it allows us not only to get a more realistic expectation of when that project will finish, but it also allows us to understand the probability of it getting finished within certain periods of time. So I'm going to use a specific example to demonstrate how to solve a problem like this. I'm not going to talk about the derivations of the distributions and stuff. Some of that will be in textbooks if you're interested, but it's not something you will need for an introductory operations management course. You'll have to know how to execute it and understand the basics of the equations. So let's look at this particular problem. A project manager has gathered info for a new project. The project deadline is 23 weeks. What is the probability of completing the project on time? So not an unrealistic scenario. You need to understand perhaps you get a bonus or incur a penalty if you're not done within a certain period, and you're trying to do a risk assessment in that circumstance. For this sort of problem, you'll get the information you've always gotten, A, B, C, D, E, F, G. The tasks are just lettered. Clearly in a project you would have a more descriptive task name, but this is an example. Over here you have the predecessors and the followers, so that you can draw the project network. We will draw the project network for this one, but we won't spend a pile of time on it because that's covered in other videos. What's different about this one is that you have 3 times for the task completion. In most cases, you would have to do estimates of these. In the case of an operations management course, you're going to be given these. You'll be given an optimistic time, a most likely time, and a pessimistic time. In the context of a real project, you would have some experience, you would estimate those, you would talk to suppliers, you would talk to contractors, you would talk to others and estimate those. You might estimate them based on previous experience. So we have optimistic, most likely, and pessimistic. So that's the basic information. From there, the first thing we need to do is to calculate the expected task completion times. One mistake that lots of students make is they just take the most likely and work from that. That isn't the approach you should take. You need to calculate the expected task completion times, and you need to calculate the variance of task completion. Completion time. The formulas are: expected time is A plus 4m plus B over 6, where A is optimistic, B is pessimistic, and C is and M, is most likely. So if you look at this formula, M is the expected completion time is a weighted average with the most weight going to the most likely. So you have 1 optimistic, 4 most likely, 1 pessimistic divided by 6. It's a weighted average of those 3. And the variance of expected completion time is equal to B minus A, so pessimistic minus optimistic, over 6 squared. So we go back then to this basic information. We know optimistic, most likely, and pessimistic. We'll just A, B, C, D, E, F, G, and expected time you look at the first one, it would be A plus 4 times 4 plus 7 divided by 6. one little trick that's always worth remembering is that if optimistic and pessimistic are symmetrically around the most likely, you can just pick the most likely. So here you have 1 to 4 is 3, 4 to 7 is 3, and so in that circumstance we know the weighted average will just give us a 4. For B, it's not symmetric, so we would do 2 plus 4 times 6 plus 7 divided by 6. So we would have TEB is equal to 2 plus 4 times 6 plus 7 divided by 6, and we would put that down here, and that would give us 5.5. That process is relatively straightforward, so I'm not going to repeat. The process is exactly the same. So we would get 3.5, 12.0, 6.5, 9.0, and 4.5. And then for the variance, again, we would take B minus A is 6, divided by 6 is 1, squared is 1. So the variance is 1, and we would similarly go through the calculation for each of the other tasks. We will get 0.69, 0.25, 1.78, 2.25, 2.78, and 0.69. So we have now expected completion time and variance of expected completion time. The next step is to draw the project network. And that is, again, a relatively straightforward process. We will go back here to the original information, and we have predecessors. We know that A and B have no predecessors. C follows B, D follows A, E follows both A and C, F follows B, G follows both E and F. So we can go now and draw our project network. I'll turn this way to give us some space. We'll draw it like we have before. The start. A has no predecessors. I'll apologize in advance for my handwriting again. It is what it is. And I am doing the best that I can. A is 4. B is 5.5. C follows B and is 3.5. D follows A and is 12. E follows both A and C. .5. So the only difference here is we're drawing the network just as we always have. We're just putting in the expected time and not the most likely time. As I said before, that is probably the mistake that is most commonly made. F follows B. .0, and G follows both F and E, and it is 4.5. Neither D nor G have any other followers, so we just go into the finish node. So that gives us the network diagram that we did when we just did it without uncertainty. The process is exactly the same. We now do the pass from left to right to find earliest start and earliest finish times, and then we do the pass from right to left to do latest finish and latest start. That process is exactly the same as it has been before. So we would go 0, 4, 0, 5.5, and then we would do 4, 16. We can't do E because we haven't done C yet. We would do 5.5 and 9. In this case, we take the largest, earliest finish time. So we have 9 and 15.5. Here we would have 5.5 and 14.5. Again, we take the highest of the two earliest finish times. So it's 15.5 plus 4.5 is 20. So we now have our pass from left to right complete. Now we do our pass from right to left. We take the largest earliest finish time, so that's the 20, 20, 15.5. We take away the duration. We have 20 here. That gives us an 8, 15.5 and 9. 15.5 and 6.5. You can see we have slack here, we have slack here, no slack here. We do 9 and 5.5, and we have 9 and 8 here. So in this case, when we go in the pass, we take the smallest latest start time, and it's 8 and 4. And here we take the smallest, so it's 5.5 and 0. So now we have our network diagram. We have earliest start, earliest finish, latest start, and we're complete. We can go through and we can see this has slack, this has slack, this has slack. So our critical path is B, C, E, G. BCEG, project expected completion time, just making sure I'm still on the screen, completion time is 20 weeks, and the variance of completion time is the sum of the variances on the critical path. And in this case, it's 3.88. It's the variance of B plus the variance of C plus the variance of E plus the variance of G. And that will give us 3.88. So now, if you recall, our question was, what is the probability that we will finish the project in 23 weeks? So for doing that, we need to come up, when we calculate the expected completion times and the variances the way we did, we know that the expected completion time is normally distributed. So in this circumstance, we're going to use the standard normal table that you've seen before in any statistics, and is at the back of almost every operations textbook, but you can also find it quite easily on the internet. And we need a Z value, and in this case the Z value is T, which is the target, minus the expected completion time over the standard deviation, which is the square root of the variance. So in this case, for Z, for being done in 23 weeks or less, this isn't exactly 23 weeks, this is 23 weeks or less, is 23 minus 20 over the square root of 3.88, and that equals to 1.52. Now, we take that number 1.52 and we bring it to this standard normal table, the standard normal table, and we go to 1.52, and you will see it's 0.9357. That's always something that's worth checking for yourself, just so you know how to do it. And so from the table, that is 0.9357, which means there's a 93.57% chance that we finish in 23 weeks or less. So if I was to ask you then, what is the probability that it will take more than 23 days? If you look at a symmetric, that 0.9357 is that area, so more than 23 days is that area under the normal curve. So you would just simply do 1 minus 0.9357 and you would get a 6.43% chance that it takes more than 23, and I should say weeks. Sorry, this should be weeks. You have to stay in the same units. Weeks. Okay. The last thing I'm going to show you is if I wanted to look at what is the probability that the project finishes in 19 weeks? Now you can use a different table and a different Z value, but because I want you to be consistent and what is easier, I'm going to leverage the fact that the normal distribution is symmetric. So this is 20 weeks. That's 19, and this is 21. So this area is exactly the same as that area, and so if I calculate this area and subtract it from 1, I can figure out 19 weeks. So rather than doing that, so I'm going to do a Z value based on 21. Z is equal to 21 minus 20 over the square root of 3.88. That gives us a value of 0.5076. I'm going to round that to 0.51. I'm going to go back to the standard norm. Oops, sorry. Back to the standard normal table. My camera tipped there, and I'm going to look at 0.51, and I'm going to get 0.6950. So I'm going to get a value of 0.6950. I'm going to, so that is this area. And I want this area, which is the same as that one. So I'm going to go 1 minus 0.6950, and I'm going to give 0.3050. So I have a 30.5% chance of finishing in 19 weeks. So if the absolute deadline was 23 weeks, I have a 90% chance of getting there without incurring the penalty. If there was an incentive for completing in 19 weeks, there's a 30.5% chance of achieving that incentive. So that's the process for doing problems with uncertainty relative to project completion time. Let's go back and just review what you have to do. A, calculate the expected completion time of each individual task. B, calculate the variance of completion time for each individual task. Draw the project network and determine the critical path. Sum the variances of the tasks on the critical path to come up with project variance. Calculate your Z value based on your expected completion time and your targeted completion time, calculate your Z value, get your probability from the standard normal table, and the process is relatively straightforward. So that is quickly the approach to problems with uncertainty around task completion time.